Okay, hello everyone. This is section 5.2, the characteristic equation, and it's a method for finding eigenvalues. So notice that in section 5.1, you were giving your eigenvalues, or if you had a triangular matrix, you know your eigenvalues are the entries along the diagonal. So here is another method for finding the eigenvalues, and it deals with something called the characteristic equation. So by the time you view this, I would have posted the take-home quiz as well as the homework is posted on my math lab for this section. Again, it's only 6 slides here, and so make sure that you read the section in the book and jot down any definitions and the theorems that you have to know in terms of understanding the things of that nature, okay? Because again, I'm not going over everything. Now, I will say the section, when you're reading in section 5.2, you can stop at the heading similarity, and then I think the next heading is like differential or difference equation. We're not going to get into that. We really don't have the time since we still have one more exam to take and only maybe a few more classes. Next week is our last full week of class, and so we really don't have time to do a lot of things that I wanted to do, but we're going to cover a couple more new things. And so here we go. Let's get started. It shouldn't be too long. Okay, so let's recall our definition of an eigenvalue. So we have some matrix, so definition like A, B. We're talking again about square matrices. So n by n matrix, lambda is an eigenvalue of A if there exists a non-zero vector x such that AX equals lambda x. And that vector x is called an eigenvector, eigen of A. Okay, and so I talked about this when you guys did the fun sheet in class. The goal is, so this is from the definition how it looks. So again, when you take your lambda, so lambda here is, actually, let me see. So lambda is an eigenvalue of that eigenvector if, when you take A times some vector x, if you can factor out a scalar and still get back that vector x initially, then we say that lambda is an eigenvalue of that eigenvector. Okay? Whereas it's the eigenvalue of the matrix A, but it's also the eigenvalue for the eigenvector. And so what we're doing in terms of, what we're doing is, in terms of understanding it further or how to solve, is that if we subtract lambda x on both sides, then we get that A times x minus lambda x equals the zero vector. And then we can factor out an x and we get A minus lambda I, or I lambda times x equals 0. And so we know this means we must have non-trivial solutions. Otherwise, that would mean that x is the zero vector, right? But by definition, x is a non-zero vector. So that's why we must have non-trivial solutions. So keep that in mind. We must have non-trivial solutions, because otherwise, in terms of this equation, if we didn't have non-trivial solutions, that means the only solution would be the trivial solution. But that infers that x is the zero vector, right? But by definition, it cannot be the zero vector. Okay, I said a lot, but I think you got me, hopefully. So using the determinant. So if now dealing with that equation that we set equal to 0, A minus I lambda, or lambda I, since lambda is a scalar and I is identity matrix, is commutative. So you can say A minus lambda I, or I lambda. Usually it's lambda I, but it's I lambda on here. Times vector x equals 0. If it has non-trivial solutions, well, what does that mean by the about the determinant, right? So remember, so thinking about, because the determinant of A minus lambda I or I lambda, what does that mean if we're saying it has non-trivial solutions, right? So again, going back to the invertible matrix theorem that tells us if it's invertible, you know, all those equivalent statements, what you need to know, especially for this upcoming exam. So you need to know those properties of the invertible matrix theorem. So if you don't have those on note cards, you need to put those on note cards because you need to know those properties. And so the property says if the matrix is invertible, then its only solution is the trivial solution. And because you know that you can take the matrix that you have and it'll be a pivot in every column. And so, which means that it is similar to the identity matrix. We can reduce it down to the identity matrix and find its inverse. And so if it has trivial solutions. So if it has non-trivial, if it has trivial solutions, that means the determinant does not equal 0. So if we are saying that we want A minus lambda I or I lambda to have non-trivial solutions, then that's the same thing as saying, well, that means we want that determinant of that matrix to be 0, right? So I hope you sort of think about that, and hopefully that makes sense, okay? So in other words, A minus lambda I should not be invertible, okay? It should not have an inverse. Okay, so the characteristic equation, what that is this. The scalar lambda is an eigenvalue of the n by n matrix A if and only if lambda satisfies the characteristic equation, which says that the determinant of A minus lambda I equals 0. Okay, and keep in mind too, especially when you're doing your homework for this section, keep in mind a couple of things. One, the quadratic formula, because you might need the quadratic formula to solve some characteristics equations. So go back in your memory bank and pull that formula up. And two, keep in mind, we're not doing complex numbers, so you only want real solutions when you're solving this. So if you don't have a real solution, that means that that lambda is not an eigenvalue for that particular matrix. Okay, so just keep those things in mind, especially when you're doing your homework. All right, so let's look at this. So we have characteristic equation of a triangular matrix. So consider the following triangular matrix A. Now keep in mind from section 5.1, theorem 1, that we know that if we have a triangular matrix, that the eigenvalues are just the values along the diagonal. So here lambda is equal to 1, 3, and -1. But let's check using the fact that we know that that means that we want the determinant of our A minus lambda I to equal 0. So let's assume we didn't know about this special theorem here. So we would take A minus lambda I, which is represented here, and then we would take the determinant just like we've done in previous chapters. And so since this first column here has a lot of zeros, we're going to use that column to do our cofactor expansion. And I have that plus sign there to show you that that first term is positive, and then the rest is just zeros. So the determinant of A minus lambda I is going to be 1 minus lambda times the determinant of what's left over when we do our cofactor expansion. So that's 3 minus lambda, 1, 0, -1 minus lambda. And that equals quantity 1 minus lambda times the determinant of this matrix here is just going to be 3 minus x times the quantity 3 minus x times the quantity -1 minus lambda minus 0, right? Because that's just going to be 1 times 0, so that's just going to be 0. And so that means 1 minus lambda, 3 minus lambda, -1 minus lambda equals 0. And if we solve, we get what we expected. So lambda equals 1, 3, -1. Okay, so that's how you would solve it. You would solve it using this method if it's not a triangular matrix, right? Any other type of matrix. If you have a triangular matrix, you could just use the fact that the eigenvalues are the values of the entries along the diagonal. Okay. All right, so this is actually the last problem. So I told you this would be pretty short, but again, go back and read the section. Hopefully you read the section first before you look at this, but I don't know if you'll do that. So anyways, find the eigenvalues and the corresponding eigenvectors of the following matrix. Okay, and so here we have our matrix A. And so if we do A minus lambda I, then we get that matrix there in red. And so if we take the determinant, because this is not triangular, right? No. So we can do a cofactor expansion, and again, we can do it on this first column here. So we'll have 1 minus lambda times the determinant of 3 minus lambda, 1, 5, negative 1 minus lambda. And so that equals 1 minus lambda, and then times the quantity, 3 minus lambda times negative 1 minus lambda minus 5, and then we multiply that through, and so we'll get 1 minus lambda times that. And then if we keep simplifying, we'll get this equation here, set it equal to 0. That factors nicely there. So we get 1 minus lambda, lambda minus 4, and lambda plus 2 equal to 0. And so our eigenvalues, our lambda equals 1, 4, and negative 2. Now to find the eigenvector, we need to put each A minus lambda I with each respective lambda. That's what that says. With each respective lambda. I know my stylus sucks, sorry. In RREF. Okay, so we need to find the eigenvector for each respective. So for 1, for 4, for negative 2. Now I'm just going to show you how to do it for 1, and I want you in your notes to finish it for 4 and negative 2. You don't have to turn it in, but it's good practice, especially before you go to that take-home quiz. All right, so let me show you. Okay, so for lambda equals 1, A minus lambda I is just going to be A minus I, right? Because it's 1. Lambda's 1. And so that means you take your matrix A and subtract it from the identity matrix for I3, and we get 0, 2, 1, 0, 2, 1, 0, 5, negative 2. Now we need to take this matrix and put it in RREF, okay? Remember, RREF is unique. So I didn't show the steps in between. I just told you that it's equivalent to, this is it in RREF right here. I want you to do the steps to verify. So make sure, I could have made a mistake, so make sure you verify by doing RREF on your own to make sure you end up with this matrix here for your RREF. And we see that we have a free variable. X1 is a free variable, and let's call that A. And X2 and X3 are equal to 0, right? Because remember, we still have, this column over here is still zeros, right? So that's saying X2 equals 0 and X3 equals 0, okay? So just keep that in mind, but because that column is all 0, we don't have to put that there. If you need to put that column there, then you can place that there, but it's not necessary. Okay. All right, excuse me. And so we have vector X, which is X1, 2, and 3, equals A, 0, 0, and we can factor out that A, we get 1, 0, 0, and voila, we have our eigenvector. And just an additional information, I didn't ask for this in the example, but if you wanted to find the eigenspace for lambda equals I, you just span your eigenvector, okay? And so you have to do this same process for negative 2 and 4. Okay, so notice this takes a little minute, so I wouldn't wait till the last minute to start that quiz. Hint, hint. Okay, we are actually done. So make sure you go over the notes, rewrite your notes, prepare. We have an exam coming up, not this Monday, but the following Monday, which means we will review next Friday. So we're going to start a new section. We're going to start 5-3 on Monday, so probably Sunday. I'll try to do it Saturday, but more likely it'll be Sunday. I'll post the notes, but you can also read ahead in section 5.3 as well to get prepared for that section for Monday. Okay, bye.